Can you see it? Okay?
Yeah, it looks good. Excellent.
Perfect. So hello, everyone. First of all, I want to thank you again, Professor Reddy, for inviting me to present this webinar, and also for the presentation. In addition to that, I want to thank you all for joining, for taking time to join to this webinar. As Professor Reddy said, I will be presenting you some results we obtained in our lab when we were doing some projects about NAPL contaminated soils. This is the outline I will try to follow for the presentation. Initially, I will introduce the problem of NAPL contaminated soils and the motivations of our research. I will briefly present the problems of particle fluid interactions when dealing with NAPL contaminated soils, and I will highlight the objectives of our research work. Then I will introduce the materials and methods we use to study this problem, and after that, I will summarize the main results we obtained on single-phase NAPL flow in soils, on particle fluid interaction processes, and on immiscible displacement of NAPLs by water. Finally, I will present the main conclusions we arrived with this research work. As Professor Reddy said, contamination of soils with NAPL is a very common problem since chemical petroleum industries require production, storage, transportation, and management of this type of compounds. The term NAPL is an acronym that means non-aqueous phase liquids. These are chemical compounds that are not miscible with water and therefore form a different fluid phase when they come in contact with water. Most common NAPLs are hydrocarbon derived fluids or organic chemical compounds. The NAPLs can get in contact with the environment due to accidental spills during transportations or as a result of leakage of underground pipes and tanks. When spills, NAPLs infiltrates downwards within the soil pores in the Badeau zones, and depending on their density, the NAPLs can be lighter than water and form pools over the water table and spread laterally, or they will continuously flow downward until it reaches an aquiclude if they are denser than water. At the pore scale level, during the flow and spread process, some NAPLs will remain trapped inside pores due to capillary forces forming ganglia. This is a very important geoenvironmental problem since trapped NAPL ganglia constitutes a very long-term groundwater contamination source because of their low solubility and low mobility. In addition to that, most of regulatory and environmental agencies all over the world allow very, very, very low concentrations levels in water. Also, many remediation techniques of NAPL contaminated sites involve immiscible displacement process. In consequence, the understanding of the NAPL distribution and ganglia formation is of key importance for having a much better understanding of contaminant plume architectures in case of leaks and for contaminant displacements during remediation. The NAPL ganglia formation and mobilization depends on the physical-chemical interaction between fluid phases and mineral grains. On one hand, on coarse grain soil particles, the capillary phenomena will prevail. So, all soil properties and factors that theoretically affect the geometry of a capillary menace or the capillary height on soil pores will have importance in ganglia formation and mobilization. In that case, we should mention and highlight the effect of particle size and particle size distribution on the pore sizes of the soils that control the geometry of the menace And on the second place, the contact angle or grain wettability, because the contact angle between the solid phase and the liquid phases defines the affinity of the mineral grains with each one of the fluids. The magnitude of the contact angle will define if the material is water wet or hydrophilic, or if it is NAPL wet or hydrophobic. On the other hand, on fine-grained soil systems, particle-fluid interaction is mainly controlled by the unbalanced negative electrical charges that are present in the phases of clay mineral particles. These electrical charges create an electrical field around the particles that affect water molecules, cations, and anions distributions that form the electrical diffuse layer around the particles. The EDL formations might be affected by the presence of NAPLs in soil pores because many of these fluids are formed or composed by nonpolar molecules and present a very relative low dielectric permittivity constant. So the objectives of our research were to further the comprehension on the particle-fluid interaction and NAPL displacement by waters in natural soils. In order to do that, we analyzed the influence of soil's particle size and on immiscible displacement fluid. We studied the consequences of the presence of fine particles in the porous media. Also, we studied the effect of grains wettability on NAPL recovery. And finally, we analyzed the consequences of the presence of soil heterogeneities on NAPL recovery. Now I will present you the materials we studied and the methods we followed to perform different tests. We used 5 different types of grain soil particles. Here you can see the pictures of each one of the particles types we employed in our experiments. We use coarse sand fractions and fine sand fractions, and for some tests, we prepare mixtures of equal amounts of these 2 types of particles to achieve a medium sand. In the slide, you can see the most relevant properties regarding grain size. Sand grains are mostly composed by quartz, feldspar, and rock fragments. We also used 3 different types of fine particles. We use lowest silt particles, zeolite particles, and bentonite particles. The lowest is typical soils from Córdoba, and it is mainly composed by silica, feldspar, volcanic glass, some fragments or particles from igneous rocks, and clay minerals. The zeolites are mainly composed of heulandite and clinoptilolite, and bentonite is composed of natural high purity sodium montmorillonite. It is important to highlight the differences in the values of the specific surface area of each particle types, as well as for the Atterberg limits values of each particle types. When we performed our test, we studied a simplified system in which we allowed the presence of only 2 fluid phases inside the pores. On one hand, we used deionized water mostly as a displacing fluid, and we used 3 different NAPLs. These NAPLs were 2 paraffin oils and a kerosene, and we chose these fluids because of their difference in their viscosity values. Also, for some tests, we employed some inorganic solutions of sodium chloride and of calcium chloride. We performed 3 different groups of experiments. The first group consisted in typical hydraulic conductivity test using a rigid wall permeameter and following the falling head technique. We tested coarse sands, and mixtures of coarse sand particles with different amounts of each one of the three fine particles soils I presented before. We prepare the specimens directly in the permeameter, disposing them in 3 layers, and the specimens were initially moistened using a 10% by weight of the same fluid that we will use to perform the test. After closing the permeameter, a fluid volume equivalent to a volume equal to 3 pore volumes of the specimen was allowed to flow in order to ensure a high saturation level of the specimen. After that, we measured the hydraulic conductivity. One different specimen was prepared for each one of the tests performed with the different testing fluids. The second group of experiments consisted in particle-fluid interaction tests. In order to do that, we measured the change on Atterberg's limits of the fine-grained particles using the different fluids and also with sodium chloride and calcium chloride solutions. To do the test, we used the fold cone method. In addition to that, we know that particle-fluid interaction processes are more evident for a particle system in the loosest state possible. Therefore, to study them, we perform rheology tests on particle dispersions prepared with the 3 different types of particles and with the different fluids. We also tested dispersions having different solid particles volume contents. For the test, the particles were allowed to be in contact with the suspending fluid during 24 hours before testing. Then the dispersion was energically stirred during 5 minutes before conducting the test. The shear stress of each dispersion was measured using different rotational velocities, using a Fungilab rotational viscometer. We recorded the data of the viscosity measurements during 5 minutes. The third group of experiments consisted in immiscible displacement test. For this test, we used a rigid wall cylindrical permeameter and plexiglass transparent prismatic cells for most of the experiments. These specimens were prepared in each one of the cells, initially moistened with a paraffin oil. After closing the cell, a paraffin oil volume equivalent to 3 pore volumes of the sample was allowed to flow in order to ensure high saturation ratio of the specimen. An immiscible displacement test were performed by displacing the paraffin oil with deionized water. Water was colored with fluorescein for the test performed in the prismatic cells to have color contrast and for being able to capture digital pictures of the flow patterns. With that pictures were digitally analyzed to identify NAPL presence. The tests were performed using the constant head techniques, and all tests were performed with a hydraulic gradient equal to 1. The fluid at the outlet of the cells were recovered in a graduated flask, and the volume of each recovered phase was determined. Now I will show you the most important results we have for this test, and we will discuss them to highlight the most important features we observed. In this slide, you can see one of the typical results we obtained for during single-phase fluid flow test. In this case, we show the change of hydraulic conductivity of coarse sand specimens having different amounts of fine particles. And you can observe how the hydraulic conductivity changes and decrease with the increase of the fine particles content, in this case using deionized water as a testing fluid. You can also observe the difference in magnitude of hydraulic conductivity between the specimens having different types of fine particles, but the equal amount of fine particles. We can see that the change in hydraulic conductivity value is more important for fine particles having higher specific surface areas. But when we perform the same test using NAPLs as permeant fluids, the hydraulic conductivity also, we observe that hydraulic conductivity also decreased with the increase in fine particle content of the specimen, but that decrease was not as important as what we observed using deionized water. And we also observed that there was almost no difference between the hydraulic conductivity measured in specimens having the same amount of fine particle content, but particles of different types. The comparison of these two figures highlights the relevance of the particle-fluid interaction that might be expected during the immiscible displacement process. So we then analyzed the results for the particle-fluid interaction test. The figure on the left shows the change on the liquid limit value with the change of calcium chloride concentration when we use ionics solutions to measure the liquid limit of the three different types of fine particles. When the ion concentration increases, thinner electrical diffuse layers are expected, and that is reflected by a decrease in the limit in the liquid limit value. That decrease is more evident or more important for the case of fine particles having higher specific surface area. The liquid limit values were measured also for the three types of fine particles using the three non-aqueous phase liquids we tested. We also found an important reduction in the liquid limit values for all the three types of particles, and the reduction was more important for the case of bentonite particles. We also observed that the liquid limit value reduces with the increase of the viscosity value of each of the testing fluids. These results of the liquid limits measured with kerosene and sodium chloride solution allowed us to compute the electrical sensitivity of the fine particles and to identify which was supposed the geoenvironmental behavior expected for this material using the classification proposed by Yang and Santamarina. From these results, it is clear that bentonite particles behave as high plasticity and high electrical sensitivity material for which important differences are expected when in contact with water, ionic solutions, and NAPLs. Then we found zeolite particles and silt particles where the behavior expected will show differences, but with less impact than the expected for the bentonite particles. Here you may see the results we obtained for rheology test in dispersions. The dispersions of the different type of particles in the three different dispersing fluids highlight the particle-fluid interaction importance for the particle system with a very loose packing. This figure change the measured shear stress with the change in the solid particle volume content of each dispersion when the suspending fluid is water. The trends observed show that the shear stress increases with the increase in the volume solid particle content in the dispersion, but also shows that the shear stress is more important for dispersion having the same particle volume content, but when the fine particles have higher specific surface area. These open symbols show the theoretical shear stress value corresponding to each type of particles at the moisture content equivalent to the liquid limit. In this case, the solid particle volume content was calculated from the moisture corresponding to the liquid limit. We also can observe that there is a clear continuity in the series for each type of particles. But when we perform the same test using NAPLs as suspending fluids, we found figures similar that the one shown here on the right. Here this figure shows the results obtained using paraffin oil as a suspending fluid, and in this case, shear stresses again increases with the particle volume content, but the results obtained for the different type of particles plot in a very near, in a very straight area. This highlights that the electrical double layers were not developed around these fine particles. The results obtained for the different NAPLs we used were very similar to this one shown here. The information presented in these figures can be summarized in only one parameter, which is the intrinsic viscosity of the dispersions. The intrinsic viscosity can be calculated using the Dougherty-Kriegers equation, which relates the intrinsic viscosity parameters of the dispersion with the solid volume particles content, the viscosity measured for each particle content of the dispersion, and the viscosity of the suspending fluid. This figure shows very small changes or differences or very similar values for the dispersions of the different type of fine particles when the intrinsic viscosity was determined for the dispersion using the NAPLs as suspending fluids. However, the difference on the intrinsic viscosity value determined in dispersions prepared with deionized water in comparison with the one obtained for the dispersions in NAPLs shows some changes for the particles having higher specific surface area. It is also important to observe that the results obtained for the silty particle dispersions show that the intrinsic viscosity determined for deionized water was very near to the values obtained with the NAPLs, and that means that in this case, or for these particles, the viscosity of the dispersion is controlled by the viscosity of the suspending fluid and not by the development of electrical diffuse layers. Then we have the results we obtained on the immiscible displacement test. This figure presents the change on the relative NAPL saturation during a water flushing process on coarse, medium, and fine sand specimens. All these tests were performed in the plexiglass prismatic cells. The error bars shown for the medium sand results represent the mean give or take one standard deviation after 6 repetitions. As you can see, the remaining NAPL content of each sample at the end of the test after 20 pore volume of flow was different, and it is higher for the coarse sand, and it decreased with the decrease in the grain size. This means that the finer the grain size, the sand grains, the lesser the remaining NAPL inside the specimen, and this is because as the finer grains are, the expected capillary effects are more important, and the more stable displacement front is expected, and that allows to have a more important NAPL recovery. The pictures we presented in these slides shows the state of the face of each specimen at the end of the test. The green areas were invaded by colored water. The green intensity, as you can see, decreased with the decrease in the grain size. However, the water distribution in the face of the specimen is more uniform for finer grains. From the pictures, we can observe that trapped paraffin oil is not uniformly distributed inside the specimen, even in the case of the duplicated medium sand specimen. These results highlights the importance of porous-scale heterogeneities on the immiscible displacement fluid flow in soils. The presence of fine particles, we mean particles passing sieve 200, has two expected effects on NAPL liquid displacement. On one hand, pore sizes depend on particle size, and therefore the presence of fine particles in the specimens will affect the magnitude of capillary forces. On the other hand, electrical diffuse layers may develop around clay mineral particles. This figure presents the change in the relative NAPL saturation after flushing the specimen of coarse sands prepared with different amounts of silty particles initially saturated with NAPL. The figure on the right presents similar information for specimens of coarse sands prepared with the same amount of fine particles but of different mineralogy. The figures show that the NAPL displacement for all the specimens is very similar, and where there is an important initial replacement of the NAPL by water during the first pore volume of flow in all cases, indicating this the prevalence of the capillary forces. After that, NAPL saturation changes very slowly with the evolution of the flushing process to almost the same remaining NAPL content at the end of each one of the tests. Please remind that the soil particles were initially in close contact with the paraffin oil, so the electrical diffuse layers may not initially develop. While water displaces paraffin oil during the test, water starts to occupy the central part of the pores until they finally get in contact with the particle surfaces. You can see in this picture the horizontal lines in the pictures represent the value of hydraulic conductivity of the clean specimens measured with deionized water for having them as a reference value. The hydraulic conductivity measured with water on the NAPL initially saturated specimen is shown in each one of the pictures for each pore volume of flow. we can see that with the increase in water saturation in each specimen during the flushing process implies an increase in the value of the hydraulic conductivity. If we carefully observe the figures, we can observe that the hydraulic conductivities of the specimens with 5% 5% silty particles, 12% silty particles, and 5% zeolite particles never reach the original values of the hydraulic conductivities because the effect of the presence of NAPL ganglia in the pores that reduce the available space for water flow with the consequent decrease in the measured hydraulic conductivity. But for the case of the specimens prepared with 25% of silty particles and 5% of bentonite particles, hydraulic conductivities measured during the flushing process reached values higher than the measured for the clean specimen. This is because NAPL is initially in contact with the particles, and at this stage of displacement, the EDLs are not fully developed around the fine particles. We also ask what would occur if the wettability of the particles changed but having the same grain sizes. In order to investigate that, we prepared NAPL wet sand, modifying the natural sand we have by coating the grains with a commercial silicone. Our grains were initially clean and oven dried, and then we sparkled them with the silicone and we oven dried again. In order to observe if the wettability had changed, we poured these sand grains in a water filled glass, and we observed that the sand grains floated over the surface. In addition to that, and to be sure, we did the same treatment on polished quartz surfaces. The pictures shows the change in the contact angle of treated and untreated quartz surface for a water drop of 50 microliters placed in an air water and a paraffin oil water systems. The change in the contact angle is very evident after the treatment. So the figure on the left side of the screen shows the change in the NAPL saturation during the flushing process in medium sand specimens having different content of hydrophobic grains. In this case, part of the mineral surface are water wet and part are NAPL wet, resulting in a mixed wettability specimen. Note that changes in the NAPL content during the displacement process are very similar for the specimens containing 25 and 50% of oil wet grains, while a significant increase in NAPL final saturation is observed when the amount of NAPL wet grains increases to 75%. The presence of NAPL wet grains forces water to partially occupy bigger pores, and consequently, hydraulic conductivity with respect to water and remaining NAPL saturation tends to increase. Finally, we perform some tests in the prismatic solve to identify the effect of the presence of macro-scale heterogeneities in the porous media. We prepared 3 different specimens, one with a cylindrical one with a cylinder in the center, the other composed of 3 parallel layers in the direction parallel to the flow direction, and the other one composed of 5 layers disposed in the direction transversal to the flow direction. The cylindrical lens, the central layer, and these 2 layers were composed either of coarse sand grains having 25% of silty particles, or by medium sand composed by NAPL wet grains. For the case of the heterogeneous samples, the water flow in front is highly affected by both pore scales and macroscale heterogeneities. The figure shows the change on the relative paraffin saturation during the displacement test. The final relative paraffin oil saturation results very close to each other, even though the immiscible displacement fronts were different because of the heterogeneities in the soil properties that induce spatial variability on the capillary forces. In this slide, you may observe how the displacement evolves in the phase of one of these heterogeneous samples composed by a cylinder layer in the central part of the layer. The sequence shows how the immiscible displacement flow evolves after 1, 5, 10, 15, or 20 pore volumes of flow. And what we observe is that the water tends to accumulate when the water displacement front reaches the interface between 2 different materials. And at the end of the test, NAPL inside the central cylinder behaves was still there, so it was not removed. At the end of this test, we dismantled the cell and carefully cut the sample in transversal sections, and we took pictures with it, of each section for digitally analyze them. The figures shows the NAPL distribution in each transverse section of the sample having a cylindrical inclusion. The red color indicates the presence of NAPL. Red means high presence of NAPL. The same was observed for the case of the parallel layer sample, which means that the heterogeneities behaves as a truly capillary barrier for the displacement of NAPL. Okay, for finishing this presentation, the main conclusions we arrived with our research can be summarized as follows. The hydraulic conductivity of some specimens, we found that they were very different as in specimens having different amount of fine particles, and the hydraulic conductivity decreased with the increase in the fine particle contents. The reduction of the hydraulic conductivity was more important for particles with having specific surface area when tested with deionized water. Yet, not important difference has been found when they were tested with NAPLs. The liquid limit and rheology behavior of particles dispersions can be used to evaluate the relevance of the particle-fluid interaction phenomenon. Immiscible displacement flow patterns show high variability even in macroscopically homogeneous specimens due to pore scale heterogeneities. The presence of fine particles in the specimens significantly affect the time required for the flushing processes, and specimens having important amount of NAPL wet particles presented higher amount of trapped oil and lower hydraulic conductivity with respect to water in comparison to some specimens with the same particle size distribution. Finally, displacing fluids accumulates at interfaces between soil layers in heterogeneous samples, and these heterogeneities behave as truly capillary barriers. At this point, I want to acknowledge my colleagues from the Groundwater and the Porous Media Research Group for their support. I share with them the daily research and teaching work, so thank you very much. And also to the former and actual grad students of our groups. Thank you very much for your attention. Again, thank you, Professor Reddy, for giving me the opportunity to share our research activities to this prestigious audience.